Hi, everyone. Nice to see so many of you. Welcome to our talk about building self-driving cars with Bazel, the second part, the scaling part. We're from BMW. We're working in the autonomous driving project, specifically in the build, automation, and continuous integration teams. My name's Alex. I'm a senior build and CI developer on this team.
So, hi, I'm Johannes. I'm lead SRE and product owner of the CI/CD system of multiple ECUs. And our talk will be slightly different than most of the talks which you already watched here at BazelCon, because we're mostly users of Bazel and also of the whole Bazel universe and the Bazel community. In this talk, we will be focusing on the build automation for our driver systems and automated driving project at BMW Group. The reason for this is that this is one of our most complicated and advanced projects within BMW. What are we developing in this project? So it's from, in quotes, simple beep while you're parking your car, if there's an obstacle or something, up to automated driving in level 3, which means that the car is responsible for the actions it's doing and not the driver anymore. Some more complexity added to our project is the corporations. For the current software, we're having a cooperation with Stellantis, former FCA. It's another OEM. We're developing the software jointly, and it's for both of our cars. And since last year, we're having a cooperation with Qualcomm, and this will bring the whole software development to the next level, because we're not just developing software for one or two OEMs, which is BMW, but together with Qualcomm, we will be preparing our software stack up to level 3 to be available for other OEMs as well. So you might be seeing the software, what we're talking about today, in other OEMs' cars in the near future. Let me quickly recap what we were presenting 4 years ago. I see the two presenters here in the crowd, Axel and Patrick. Welcome back. So 4 years ago, or actually 4.5 years ago, we were facing quite a bad situation. We had roughly 200 individual repositories, a lot of developers only having access to 4 to 6 repositories, doing their component. Changing interfaces or anything was hell. Integrating code was really cumbersome, and finally bringing your software, your changes to the car, yeah, it was really painful. Then we did 2 major changes. One change was that we took all the software from those 200 repositories and brought them together into one big virtual monorepository. We're using Git with Git submodule for this, and currently we're having roughly 40 submodules. The only reason why we're not having one specific repository is visibility rights, so legal rights, because we're cooperating with quite some partners and not everyone is allowed to see everything. That's the reason why we use Git submodules. The second and potentially most important change that we did is switch from CMake and Catkin environment to Bazel. And that's exactly what we presented here 4 years ago. So we were able to have incremental builds finishing after 10 to 15 minutes and not waiting till CMake and Catkin did all the iterations, all the loops for like 60 minutes if you just changed one line of code or maybe did just a change in a README or something like this. What happened in the meantime? So 4 years ago, we were presenting the results. We didn't have a car there yet, but now we have cars on the road. Let's call them Bazel cars. So the software for at least 2 of the ECUs in all of those cars is being built and tested with Bazel. Some of those cars even are having up to 4 ECUs with Bazel. Some of our flagship cars, especially the iX, the iNext, already presented in the last talk as a prototype. You saw it fully camouflaged. Now it's out. You can have a look. Also the i7 series with the really huge panoramic display in the back. And quite recently released the i5. If you go for the i5 M60, you have close to 600 electric horsepower, which is quite awesome in such a sedan car. This is not all the cars which are Bazel cars. So we have quite some others like Alpina or Rolls-Royce. It's just there are Bazel cars out there, quite some of them. So when you see them driving around, this is all thanks to this community that we were able to ship the software to those cars. But the success of our workspace also is a problem because since we were able to ship in time and also properly tested software, more and more ECUs, more and more developers, more code came up because people wanted to join our workspace. They wanted to join our infrastructure because it just worked. So the difference from then to now is that we are having more than 3 times the amount of code, more than 3 times the developers. And when we're talking about developer, that really means each of those persons has at least 1 commit in the history. That's how we extracted the data. We have a lot more developers who are doing requirements management and not touching the code, which is also super important. But really, each of those 6,500 developers has at least 1 commit. 8 ECUs in the meantime, plus 1 classic AutoSAR software development project, 4 times the number of builds, a lot more CI developers. And I think what you also see here down on the graph, the most impressive number is that our resource usage of the CI is 12 times as high. So at the time when we had to talk 4 years ago, we had roughly 3,000 vCPUs peak usage. Currently, it's 33,000 vCPUs peak usage. And this rapid growth, this rapid scaling brought a lot of challenges with it. And the most interesting ones, just some of them, will be presented to you by Alex now.
Thanks, Johannes. Grab the clicker. So let's talk details. Before we do that, let's talk about our CI setup to make sure everyone's on the same page. So we're using Zool, an open source CI system for our CI. With Zool, you have the concept of jobs, and you can all think of a job as a set of steps that run in quick succession, with one of those steps being Bazel test ... We also have the concept of pipelines, and pipelines are triggered on specific times across the lifecycle of the pull request. For example, the pre-merge pipeline, that pipeline's triggered when a pull request is initially opened. Post-merge on the right, that's triggered after a PR is merged. And the one in the middle, the merge queue pipeline, that's similar to pre-merge, but there's something special, which is when all of the changes that currently want to merge, they're all bundled together and tested with each other to make sure they're all compatible. And if one is not compatible, that change is ejected from that queue, and then everything else has to restart without it. So talking more about jobs. All of our jobs run on virtual machines that are spawned in our cloud regions from scratch. And after the job finishes, these virtual machines are destroyed. They're gone forever. So we call them dynamic CI nodes, as opposed to static CI nodes, which last for forever or for a longer period of time. A CI job can be broken down into a few phases. So pre at the beginning, which is where we clone the source code, set the git state, and so on. Post at the end, where we pass the Bazel output and upload all of our metrics. But the bulk of the job is always the main part in the middle, and that's where we run the expensive Bazel commands. Talking more about Bazel, so our monorepo is pretty big. You heard from Johannes. We have 300,000 targets, a lot of external repos, over 200 gigabytes. So you can already imagine fetching 200 gigabytes in every single build 80,000 times a day. It's going to be expensive, or it's going to bring down our network. How do we solve this? We use the concept of disk images, or with Zool it's called node images. What we do multiple times a day, we build a disk image and we bake into this disk image the output of a Bazel command, so the output base with the external folder, everything already extracted, the exec root, all of that. We also bake into the disk image the operating system, so Ubuntu in most cases, also other certificates and configs and packages and so on. And then with this disk image, we upload it to our cloud regions, so on-premise and AWS, so that every job which starts up in these cloud regions can use this pre-built disk image, and everything is immediately present on the file system when those jobs start. Talking more about pipelines. So the pre-merge pipeline is the first pipeline that a pull request encounters. But before that pipeline even starts, we do have another layer of defense we call puts-a-fish. You can think of puts-a-fish as a microservice which runs in the cloud, and it listens to events from pull requests and can run super fast linters on the files changed in the pull request, like Builderfire, Python format, and so on. The downside is it operates on a per file basis, so it of course doesn't have the context of the rest of the Bazel workspace, so it's limited in some ways, but feedback is just a couple of seconds, so perfect for developers. Once that succeeds, the real pre-merge pipeline can start, which spawns the job, starts the virtual machines, and so on. In the pre-merge pipeline, fast feedback and developer velocity is really important. So we only run small and fast tests in this pipeline, or tests with a short or moderate timeout. We also have some other quality of life checks in this pipeline, such as checks to prevent the prevent Bazel query from being broken, prevent the analysis phase from being broken, and so on. We also have other checks which are configured via YAML. So some examples down here, which prevents bad attributes from being added to targets, or bad features and so on. And most importantly, we do have a dependency checker to prevent the so-called spaghetti workspace from being from becoming a thing. This is also configured via YAML. And so for the prominent scopes, you can say exactly what the scope is allowed to depend on. And then if a user introduces a dependency which is not allowed, the check will fail. If it's valid, then the user can, of course, add it to the whitelist. But if it's not valid, then the user has to break that dependency. One key challenge that we've encountered over the years is flakiness. So infrastructure flakiness, namely, this is most common. This is most commonly downloading external repos from anywhere. Really, there can be network hiccups that interrupt the download and cause failures. To sort of mitigate this, we developed a tool called Smart Retry, which you can think of as a wrapper that wraps around Bazel, and it detects the output of Bazel, and if there's a failure, it's able to classify the failure into either a compile failure or an infrastructure failure. If it is detected or classified as an infrastructure failure, then the exact same command is run again, keeping the Bazel server alive, the analysis cache hot, the cache on disk hot as well, which is much better than the job failing and the resources being wasted. It's also able to dynamically change the commands, or add or remove flags. For example, if a flag was the cause of a failure, it can be removed, or if a flag could be added to mitigate a failure, it will be added. The example in the top right is when Bazel goes out of memory, or the JVM goes out of memory. Smart Retry is able to dynamically reduce the jobs for the next attempt, so that less jobs running in parallel means less memory being used, with the hope of not going out of memory. So moving on to the execution phase, we have a big workspace. Compiling just the business logic from scratch on a 32-core machine takes at least 6 hours. So of course, caching is essential. We do have the local cache in the disk image, which I just mentioned, but this can become out of date very quickly. For example, the duration when you start building a disk image and when it becomes available later on, this can be many hours. So the content inside the disk image, it can be out of date quite quickly, depending on, of course, the changes that were merged in the meantime. One level up is remote caching. For us, we use build-on, which we really like. What we worked out very early on is that cross-region traffic is never a good thing. And on-prem and AWS as well, we have many different cloud regions. So to mitigate cross-region traffic, what we did is we set up one build-on instance per region, which was great because it avoided all of the cross-region traffic. But it did mean that for every cloud region or every remote cache, you had to build and upload the cache hits n times for each remote cache instance, which was not great, especially in pipelines where developer velocity was very important, like the pre-merge pipeline. To solve this, we developed a bit of logic called smart target picking, which was inspired by a prior BazelCon talk. The gist of smart target picking is look at what files have changed in the pull request, work out the targets affected, and only build and test those targets. A quick overview of how it works. There are 4 central steps. The first step is git diff, so pretty self-explanatory, work out which files have changed in the pull request. Second step is Bazel query our build files, so work out which build graph files directly depend on the modified files, so like build files or .bazel files. Third step is Bazel a query, so work out which targets have the modified files as inputs. And then finally, cquery reverse dependencies, so essentially work out the indirectly affected targets of the directly affected targets. In most cases, actually, where you don't invalidate the whole universe. So the example on the screen, if you just modify a README file, this is perfect because nothing's going to get built and tested. This is super fast. Or if you just modify like one test or something, only that test is going to be built and tested, irregardless of which region your build's running in or which remote cache you're using. That's really fast. But if your change invalidates the whole universe, yes, the whole universe has to be rebuilt, which is expensive. Talking more about the execution phase. So another pain point in the past was determinism and hermeticity. So you can think of non-deterministic actions as actions where you build it once, it outputs one thing, you stay on the same Git shard, and you build it again a second time, and the output is completely different. So this ruins caching, and it has to be recompiled over and over, and it's not great. In our experience, this is mainly due to generated files. So baking into files timestamps or IDs or paths, or the classic iterating over an unsorted data structure. This produces non-deterministic files. Also, non-hermetic actions, so actions or targets which depend on something on the host, or just in general, the dependencies or inputs aren't correctly modeled in Bazel. This means, or this for us anyway, resulted in very hard to debug remote cache poisoning issues. And of course, the big one, these actions can't be executed remotely because that dependency is not present in the remote worker. For non-hermetic actions, it's quite easy to work out what's hermetic and what's not. You can just try and run it remotely and see what fails. And for non-deterministic actions, there are some features in Bazel that can help you detect non-determinism, such as the execution log binary, which we use. Another pain point is test flakiness, so different to infrastructure flakiness. This is when a test fails sporadically from time to time and for no reason. For us, this is mainly due to tests which are multi-threaded and require more compute resources than one core can provide. And of course, if you run as many of those types of tests as you have cores, then those tests are going to exhibit undefined behavior. Also, we've had in the past general issues with test frameworks, which made them flaky, and so on. And of course, there's many other reasons. To detect this, there's quite a simple approach, is brute force it essentially. So overnight, we have a lot of idle on-prem CI resources, and what we did, we ran all of our tens of thousands of tests overnight on those idle resources to work out what's flaky and whatnot. We also track this kind of data in the normal, or the regular pipelines, like the pre-merge pipeline and the merge queue pipeline. And with this data, we can make certain assumptions. If it fails in the pre-merge pipeline, if a test fails in the pre-merge pipeline, it's actually okay, because that's the point of the pre-merge pipeline, to see if your change breaks a test. But if a test fails in the merge queue pipeline, it's either because there are two changes which touch the same part of the stack, and those two changes are incompatible with each other. That's also the point of that pipeline. But if it happens too often, we can maybe say this test is flaky, this test is broken, and we have to act. How do we act quickly? We developed a tool called the Auto-Sheriff, which was also inspired by BazelCon in the past. The Auto-Sheriff looks at all this data generated from the builds, and it automates a lot of actions to deactivate these tests. So it's rule-driven, like most of our other tools. On the right, you have an example of a rule called mark as flaky. A rule can be broken down into a condition and an action. So the condition in this example is if a test has failed more than once in the merge queue pipeline, and if that condition is true, the action is triggered. In this example, the action is use bulldozer to set the flaky attribute to true on the affected target. It's also able to automatically open up a pull request, which then a human can approve and merge. Some tests, however, they're just too long running or too flaky, so they can't be in these pre-merge pipelines because it would affect developer velocity too much, so we put them in the post-merge pipeline. But the challenge for us is, as these tests are not tested before a pull request is merged, how can we ensure when someone breaks a test and they only know about this many hours after their pull request is merged, how do we ensure that they fix it? For this, we developed a process and platform called Track and Fix. You can see an example of this on the right. And what it is, it sort of visualizes the tests that some of the feature teams own and provides the status of each test. So is this test broken? Is this test freshly broken? Is this test flaky? And so on. because we upload data in every single CI job and every single pipeline, it's also able to provide a best guess as to which change broke a test and contact the test owners to try and fix it. Finally, monitoring and profiling, extremely important for our team. So we pass all of the output from Bazel. We upload this data to Elasticsearch, our database. Also, any of the files outputted by Bazel, we upload this somewhere where feature team members can download this afterwards, like test logs and so on. We also do SAR logging. So with SAR, you can see exactly what's being done on the VM at every millisecond. And finally, Bazel profiling, extremely important for us. We also use the no-slim flags because we think that we get all of the data with that, and it's really important. We also do some post-processing of the Bazel profile to sort of filter in or filter out parts of the profile we don't necessarily care about. And then we upload it to Elasticsearch, where we can create aggregations and visualizations like what you can see here. Like, for example, on the right, we can have the sum of the duration of all actions in a profile broken down by mnemonic type. So you can see what Bazel's doing for the majority of the time, like in this case, 50% compiling, 20% test actions, or even break it down on a per target or a per file basis, like on the left. So we know if a particular file, if it spent a lot of time compiling, that allows us to focus our efforts and maybe dive in and see what's wrong with that file. There were many other problems, but we don't have time. So I'm going to hand it back to Johannes to talk about the future.
Thanks, Alex. As Alex already mentioned, so this is just a very small number of challenges which we were facing, which we think we already have solved. Please let us know afterwards if you guys would be interested that in one of the next BazelCons we might go into some more challenges. We are still facing a lot of challenges, actually, and just to give you some idea about the major points we're currently working on. So one is remote execution. We're together with Engflow, we're currently evaluating their software as a service setup or solution. Regarding performance, as you can see on the bottom of the slide, it's really way faster than a 6428 core machine on AWS, which we used as a reference here. Currently, we're still in evaluation of the stability and the cost, because cost is a really major factor for us. One thing to remark here, if you still have a Bazel workspace and you're maybe starting small or you're starting setting it up, please ensure that right from the beginning you take care that it's hermetic, because for us it was a major pain point to make it hermetic. It took more than a year to work on it, and it's still ongoing. Another thing we're working on is smart resource and smart job picking. Smart resource picking, you can imagine that we're running some queries, because for every change, for every pull request a user is creating, we're running like 10 to 120 jobs, depending on which repository, which folder this pull request is in. And with smart resource picking, we're running a query to evaluate how many build and test targets are there to be built and tested. And depending on the number of targets or tests, we choose the size of the virtual machine. So if, for example, only a README or one test is touched, we could run on a 4 or 8 core machine. On the other hand side, if the whole universe needs to be built or tested, we are starting up a 6428 core machine to be faster. Next step would be smart job picking. Smart job picking goes even one step further. You can see an example at the bottom of a first implementation. So instead of starting up the VMs, also if it's just a 4 or 8 core machine and setting up the workspace and everything, we just don't run the jobs if it's not necessary. So we can save a lot of resources and have faster feedback. Machine learning is a big topic on our side. We're using it for faster developer feedback and to reduce CI costs. So one use case, for example, could be to identify if a change has a low likelihood of failure, so that it will succeed, and then we put it in a fast check or a fast gate pipeline. Or on the other hand side, if the likelihood is very high for failure, we can have a multi-stage check on it to save resources. And last but not least, CI cost is a major challenge for us, as you can imagine, with so many resources being used. We have a high 7-digit budget for only the cloud resources currently, and we're pretty happy that we didn't make it to 8-digit this year. It's a big challenge. We're practicing FinOps, just started on it, but we have to bring the cost down. last but not least, and one of the major things what we want to address here is, without the migration to Bazel and without you as a community, not just the people working on Bazel and bringing Bazel forward, but also the whole landscape around it, like Build Barn and whatever, we wouldn't have been able to be at that scale where we are. So big thank you to everyone of the Bazel community. We heard Build Barn was a major contributor here as well, but also a big thank you to everyone within and sadly sometimes outside of BMW now to contribute to our workspace and make this happen. And side note, we are hiring, so if you're interested to have some CI Bazel at big scale, please contact us. Thank you very much. We're open for questions.
Yeah, hello. I'm just wondering, was there a specific reason why you chose Zool as your CI/CD framework?
You want to answer?
The main reason was Zool is very good at with using multiple repositories and gating those changes from multiple repos together. Other CI systems is mainly like one repo based, but with us we had so many, like 20, 30, 40 repos. We need to gate those changes together, and Zool, it calls itself the gatekeeper, so it's really excellent at multi-project support. Excuse me? Can you hear me?
Can you answer? We can't hear you, but if you speak up, we would repeat the question.
Yeah, something tells me it was a deliberate decision not to use. So something tells me it was a deliberate decision not to use static CI.
If I may, so very good question. So we had definitely more than one POC on static CI workers. We actually do have static CI workers. So we're running some tests on hardware workers, for example, and some other tests on QEMU machines, which we were not able to put them on top of our open stack setup because twice virtualization was very bad. So we are running static workers in our environment. They're having their specific problems, and that is also the major problem why we decided against static workers, because you always have to watch out that static workers are in a proper condition, and that whatever a developer is doing, and our developers in our CI config repository can play around and test whatever they want, that they leave the static worker in a proper state, that the next job which is running on the static worker does not have any issues running on the static worker. In the POC, we did some cleanup and some major work and make that happen, but to be honest, we failed. So we stayed with our dynamic nodes because you can ensure that the dynamic node is always in a state that only the change of the developer is run against a ground truth and not what somebody in front of you has left.
Hi. Could you elaborate in one of your future plans? You mentioned you're looking to skip builds that are predicted to succeed. Could you elaborate what that means and how you're going to do that?
So what we're having in mind, it's not implemented yet, we're working on this. What we're having in mind is, Alex presented to you that we have pre-merge checks, like a check pipeline, a gate pipeline, and then we have post-merge checks. And the idea behind this is that for fast developer feedback and getting stuff integrated as fast as possible, if the likelihood is very small that a job or a test is failing, that we take it out of the pre-merge checks, but rather test it afterwards and use our processes like the track and fix to identify if something got broken. And worst case, it would be automatically reverted to change and the user would be informed. It's all about developer feedback and getting stuff integrated as fast as possible. Because currently we're having, I think on average, 500 pull requests being merged per day with a growing number. And at this scale, it's difficult to avoid concurrent changes and enable developers to do a fast integration.
Right.
Hey, great talk, thank you. I'm curious if you looked into any tooling to inspect the dependency graph to see if there are any optimizations there that would prevent running unnecessary tests. I figure in a large code base this would be relevant. Many thanks.
Yes.
Would you be able to share any insights? Thank you.
I mean, dependency optimization, that's always a topic. And we try to protect it from getting worse with the dependency checker, but we haven't really found capacity yet to like break the existing dependencies and optimize them. But it's always on our radar. It's always something that needs to be addressed.